Today I would like to shift the gears a little bit and talk more specifically about computer science than about mathematics. But first, are there questions on the homework assignment that I should get out of the way? First, everybody understands it fully, well enough to come to the TA office hours this afternoon if you don't? Right. Okay, good. So computer science is the the name of the department that's teaching this course is CS 209, and it's called mathematical writing just because we didn't really have an adjective in English saying computer scientifical writing or whatever the right word should be. Maybe there never will be a word for it, but computer science is a big mouthful. But we haven't. But informatical writing, would that be the proper European term? I don't know. Well, it's in other fields that use mathematics that aren't specifically doing central mathematics. You still have all of the problems that arise in mathematical exposition, but you also have other ones. And it turns out that, for example, a typist, a technical typist who has to work for the computer science department has to know everything that a typist in the math department has to know, but a lot more about, because there's algorithms that involved. I mean, this sounds chauvinistic to say this, but I've been involved in hiring typists, and it's just and so I want to try to explain some of the things that make computer science an extra add-on complexity to the problem, and then discuss some of the answers that are showing up and so on. So I brought a bunch of stuff with me, and I'm not sure I can find all the right materials in time. Unfortunately, I didn't give myself enough time to locate everything. My first example was going to be based on Polish mathematics, and I had remembered something incorrectly. See, your homework problem is based on a paper in a Polish mathematics journal. So I thought this would be a nice continuity, because I published also in a Polish mathematics journal, and I included algorithms in my paper, and so I was going to show you the way they screwed up when they tried to typeset my paper, and the algorithms came out looking terrible. Well, I found out as I was looking through the files just before class that they didn't do such a bad job after all. And so I had to go to some more files to get the proper examples. It turned out that when I wrote a letter to, this is a journal called Acta Arithmetica, and this letter was dated 77, and I did write a letter to them saying, just describing the fact that I'm using floor and ceiling functions that they didn't have in their journal, and so I was making an argument for them to do that. So in the paper, in the proofs that I got, I had to tell them where to lop off the corners of these symbols, and this is all hand set in metal type and so on. This is you can see it's Polish, but then when I got to the algorithms where I thought I was going to find that they had great problems, it turned out I had anticipated the problems earlier when I sent it in, and so I marked my manuscript up very carefully so that they wouldn't get that they would have that working out pretty well, although there is some indentation and the number 6 was missing here and so on. These are the galley proofs, but they didn't. But this came out reasonably the way I wanted, and the mod operator here should be in Roman type. They didn't. They just made it as one long identifier, K mod H. But but otherwise the most common mistake that a printer typically makes when you send them something and don't mark it up carefully is this colon equal sign. Now, they'll love to put the colon far to the left and then a space and then an equal sign. But So this wasn't the example that I wanted, that I was expecting it to be. Now, these conventions for typesetting algol-like languages were developed by the ACM. Myrtle Kellington was the executive editor of ACM Publications through the 60s and spent a lot of time developing standards for indentation and boldface, italic. When you go into Roman, like comments will be in Roman, identifiers will be in italic, except a numeral will still be Roman, sigma 2, and she worked out putting the colon and equal sign together and so on. When algol was defined, there was no thought given to these questions of how to actually typeset it, but Myrtle was in on it from the very beginning of publishing the report and worked on it together with Peter Nauer in order to get something that looked well. So when Algol 60 was published in 1960, it had a nice looking report, and it was due to this special work, and it can only be appreciated by knowing how many things that was different from what the typesetters were doing otherwise. Now, I think I do have an example in the other folder here.
Question?
Yes.
Are you going to discuss, like, could you give a reference for that, or
to which now?
For the business about why it's boldface, why the
oh yeah. Now, I don't believe she's ever published her pages of style rules for setting algol type. She just, she gave it to the people at Waverly Press and other journals that want to publish algol-like languages have written to ACM and gotten it from their headquarters, but I don't think that's ever appeared in print, these style rules. Maybe that's not the question you're asking now.
Well, I'm wondering.
Yeah.
Basically, I've always wondered why people want the predefined words like if, and, procedure, and so on, boldface, and the other things are supposed to be not boldface and so on. I was wondering if you were going to discuss that.
Okay. Well, it's something that seems to read better if there's a way if there's a way for them to be typographically different. Now, I haven't seen all the different possible experiments that went into it, but having the okay. I guess I should say something about if you look at the old publications before Algol, what algorithms looked like, I think that would probably be the best answer. But the hardest thing, let me see. Fortran was all caps, and they would typeset all caps, and caps on the typefaces were not made to look good when they were used in such and mixed with numbers and parentheses and things like this, and have a long pieces of text in all caps, not having a fixed width font was a loss, because in Fortran you needed to know what was in column 5 and of the card and for a comment, or was it column 6 or 4? I forget. When you punched the cards, anyway, people would. There were a lot of papers published that used that needed a fixed width font in order to make it make sense, and the programs always looked pretty awful if you just had them all caps and things like that. Now that was the environment before Algol, and with Algol they decided that there was a concept of reserved words, and so these words begin, procedure, so on were to be different from the identifier begin and procedure, which were legal identifiers if you look at the original definition of Algol. And therefore the original implementations of Algol required you wouldn't just say BEGIN in your program, but you would say, I think it was like @ BEGIN in order to mean this is the reserved word BEGIN, as opposed to the identifier BEGIN, which you're also allowed to use. So you were supposed to have some way of, and the compiler was supposed to treat this as if it was a single letter, each reserved word was, in the definition of algol, strictly speaking, a equivalent to the letter A or B or something like that. It was a letter of the terminal alphabet, terminal symbol alphabet for the language. And it wasn't until a couple, some years went by before people realized that it would be much better to reserve the reserved words and not allow them as identifiers. But in Fortran, there's no such thing as a reserved word. I mean, you can have a variable called do5i, and do5i equals 3 is different from do5i equals 3 comma n, because the latter is a do statement. The first one is an assignment to the variable do5i. And these conventions for actually delimiting and separating out the functions of things developed about then, and I think it's turned out to be a useful key, a useful way that, and even though you're using you're using bold, Roman, and italic, they seem to mix in a way that psychologically blends with our understanding of the reading. So I don't know. Now let me see if I can find the one in the example of a typesetter who hadn't gotten who hadn't done computer science before. I'm not sure this is the right. Yeah. Oh man, this one's really awful. Okay, good. Okay, and this turned out. This is, in fact, is the American Mathematical Monthly. So surprisingly, these are galley proofs from the Math Monthly in 1984. So actually fairly recent. Here I'm describing using an algol-like language where I'm describing some of Eric Bishop's constructive mathematics, which is a book that writes where every proof in it is really an algorithm, but his algorithms go way beyond the normal data structures of computer science. And I tried to put it into a computer science. I tried to put his mathematical language into computer science notation from one of the pages. I guess I tell you what this article is. It's called Algorithmic Thinking and Mathematical Thinking, and it's trying to analyze what it is that mathematicians do, and is it different from what computer scientists do. And I took a sample of books, and I looked at page 100 on each book, and then I tried to boil down what things would an AI program to do mathematical reasoning have to learn in order to be able to handle page 100 on these various books. And one of the books I chose was a book of constructive mathematics, assuming that maybe there would be some difference between that and the mathematics written by other people. Well, now, so I try to do this in a computer language. So here you see one of the first things that typesetter doesn't know, to put the colons next to the equal sign. Here they used a very funny symbol I had never seen before, with that a little tiny little dots after the equal sign, completely wrong. But they maybe were trying to get something on this. And then lemma 5 here you see is in Roman. Here it's in italic. It's got to be consistent between the two. And when I got to when I got to this one, it really started to break their system. I mean, look at these lines smashed into each other. This is that an upside down question mark? I don't know. Everything is all screwed up. So now when you finally see the article in print, it might look like it was simple, but the actual formatting of this was sufficiently different from what these people who do mathematics every day normally do, that they just was sort of terrified by this. But I was talking about the different data structures. Now you see, here's a data structure where the variable is a function that takes one parameter times itself into the positive reals, and so that's a data type or for a local variable of this procedure. And people who were in my 304 class last year, where we talked about complicated data types, who will recognize some of this as I mean, this type lambda calculus is now becoming an important research topic. But anyway, I'm talking here about the method of presentation, just to illustrate that there's style rules, things that go into these that are fairly extensive and not the same as ordinary mathematics. So this is one add-on to mathematics. Now another thing I alluded to that computer science seemed to need that mathematics didn't have was the idea of a style of type with fixed width. We refer to strings of characters, and we refer to things that person types on a terminal, and these appear on a screen, usually in a font that has fixed pitch, so that things will line up below each other on adjacent lines. Now, so when I came to publish the volume 1 of the Art of Computer Programming, the publishers said it was going to be impossible to have a fixed width type. I would have to use variable width because they were doing it with monotype, and monotype had room for 256 characters, and they had to be a certain thing, and they already had bold and italic and Roman. How are they going to get another style in there too? But I was very insistent that it was going to be important to have something like this, and so the people at S and Wesley went down to the shop, and finally they worked out a system where the guy says, yes, we can figure out how we can throw out some of these Greek letters you aren't using very much as often, and we'll put those in by hand, and we'll put in a fixed type. And they found a nice style of type that would blend with the other things well. I think this is the original monotype thing where they mix this typewriter style with italic here and with Roman and then there's bold also here. And the one change I had to make was that we had to be able to tell the difference between O and 0. And so though this O here was specially designed for my book to be very square, to distinguish it from the 0, which must appear somewhere nearby here. Here's a 0 down at the bottom here. So the O was made specially for this book in the 60s, and then they figured out a way to actually put these things. I was using words like contents and so on in a technical sense where I wanted something to be typographically different. The most important thing was I was defining an assembler language where the fields were important as to where things appeared in columns and so on. So fixed width was important at that time. That still seems to be true today. That is, when you write a manual about computer programs, it's quite often the case that you'll want to have the examples that reflect something that you type into the computer, or that the computer shows on a screen or something like that. You'll want that in a specific type that will be a fixed pitch and will be specific. So this was now we intentionally in the 60s we confronted this and said, does computer science is a the first computer science programs have just been established. Are there any things that make it different from what other journals are doing, computer science journals, that ought to be thought out and experimented with? And we faced this consciously in those times, and the typographers came up with these solutions, and they're now still with us, I guess. Okay, let's see. I had several things I wanted to bring up today, and I'll probably come out in peculiar order. But the presentation of algorithms is one of the main things, of course, that distinguishes computer science from other things. We have to describe how we present a method, and was writing this series of books that I knew was going to take me many years to finish, and the question was, how was I going to present the algorithms in these books? And I knew I wanted to have one level that was very low level, so that the ideas about going from a low level, machine level, up to higher level would be clear. But what should I use for the high level language? Programming languages in the 60s were in a terrible state of flux, and still they are. I mean, we still don't have everybody's favorite programming language. Hasn't come along. And so I knew that if I took a particular programming language, I would alienate 70% of the people who were going to read the book, and even in the others, they would probably not have that language implemented on their machine, and so they would think they shouldn't buy the book. So I wanted them to buy the book. I wanted everybody to buy the book. So I decided not to use a programming language, but to use English instead. And I'm going to discuss the pros and cons of this. But later on, then Jeff Ullman and Alejo Hopcroft came up with their book, which covered many of the similar topics, and they decided to use Pigeon Algol in their book, which worked successfully. It was sufficiently different from Algol. Nobody would ever try to actually type these programs in and run them, but it was still expository. By that time, people were used enough to that kind of language that they felt it was reasonably readable. Still, I've gotten many letters from people saying that they appreciate the way that I give algorithms in English, because then they actually read them. It looks like it's something to read, and so they read them. They get caught, they don't realize it's going to be, but they actually do read them, and so they said that was a good idea. And so I get this. So the style I decided to use in these books was based on something that I had actually seen in the Russian literature in the 50s, where an algorithm was given schematically with a flow chart that had very little detail in the steps, but it gave a picture of what was going on. But the idea was that you had one or two keywords in maybe three in this case. Here's 1, 3, which would describe the purpose of that step, and if you understood the algorithm, this would be a helpful flowchart. It wouldn't be good enough by itself. But then, so I kept these keywords in the at the beginning of the step, and the keywords end with a question mark if there's a sort of a test going on, and a period otherwise. And I tried to find these two words that would boil down the whole idea of the step. And then later on, this would also make a reasonable comment to put in an assembly language program. E1, find remainder. And so I decided for presenting an algorithm, I would use something like presenting a theorem. It ended with this black symbol that I also use at the end of a theorem. And I give a title to it, like I give theorem A, I would have algorithm E, and I would give a description at the beginning, the way a theorem has a description of what's going on. In the algorithm, I'm just talking English here, so I'm not making assignment statements or anything. Although assignment statement, I guess so. I have this left arrow operation, which isn't exactly English, but needed that. That's something that computer science has that mathematics doesn't have. Then there's parenthetical remarks that state things about the algorithm that turn out to be useful. But not, useful to understand it. And as I learned more, and the years went by, I learned more about the the idea of invariance, and so the comments on the algorithms I wrote after 1968 or something like that would be consciously done with the idea that the things I'm putting in parentheses are often the invariance that a person would use in a formal proof of the correctness of the algorithm. So anyway, now this was the style of presenting algorithms that I used in the book, and I'm going to continue to use it. On the other hand, I can't consider it to be a success because of the following thing. People have tried to copy it, And you might say that's a mark of success, but the fact is that none of the copies that I've seen do it well. At least I don't like the way they've done. They copied this style, and they said, and unfortunately they say, now I'm going to present an algorithm in Knuth's style, and then they proceed to botch my style completely. I mean, all of the things of it that I consider important, they change. And so the fact is, then, it must be a personal style that only works for me. So you should find one that works for you, but don't say that it's mine then. That's okay. But in more recent papers, I have been in my books I've adopted this style. The book, The Art of Computer Programming. This is a project I started in 1962, and maybe 20 years from now I'll finish it. So it's a long, ongoing thing. I can't just up and change the style every so often. But in the more recent papers that I'm writing, I'll be using a style that's where as I showed you, I had algo-like languages here in the paper, and I'm. In fact, this is very close to algol, except every once in a while it uses, well, I'm not sure, this divide operation. Every once in a while, if mod maybe wasn't in algol specifically, but Pascal has it, but Pascal's mod is flaky. So anyway, I'm still using an algol-like style in this article. I'm intended to do that as depending on the class of readers that I assume. Okay. Now, I've got a handout which for what I would like to talk about on Wednesday at some length, possibly also it'll carry over to Friday. Can we pass these out to Tracy? Actually, we got a whole bunch here. Why not overdo it? And the handout is based on an idea that I've been trying to push called literate programming. And this was an article then that John Bentley wrote in the Communications of the ACM. This was May 86, where he did me the great favor of popularizing my ideas in one of the best American journals for having a lot of readers. And this is called Programming. Yes, Guest Oyster. This is called Programming Pearls, and he said it was a special guest oyster. John is a good writer. Now, tell you now. I hope you read this in between today's class and Wednesday. I'm not going to read it to you now. But I did write this article before in the Computer Journal, and I got a note from John Bentley saying, "Why did I publish this in the Computer Journal? Because Americans ought to read this, and they never read the Computer Journal. This is the British Computer Journal, British Computer Society Journal." And I said, "John, I wrote it in the British Computer Journal because I thought Americans were illiterate and they would never care about this sort of thing." It was only people in Britain that know anything about writing, and in fact, I waited until I had a trip to England. Until I was going to England for, I guess that's the trip to Wales that I mentioned last week. When I was going to the British Isles, I saved up. That was the time when I gave a talk launching this idea, and so in London I gave a talk to the British Computer Society called Literate Programming, and I think that this is one of the biggest ideas to come out of my work on tech, actually. So I'm rather proud of this. If you don't like it, try to conceal that fact from me, because as you see, I'm tickled pink with the idea. But I found that as I was facing the problem of how to explain the tech program to a wider audience, that this forced me to think about presenting a program in a different way than I'd ever done before, and the way that I finally started writing it when I did the second draft of tech was was for me a radical change in the way I write programs, and for me I had finally discovered the right way to write programs after 25 years, and I wanted to go back and rewrite every program I'd ever done in this new style, and I was really thrilled with the way things were working. Something clicked. It was a bunch of old ideas that when you put together in this package, all of a sudden they all worked very well for me, and so I got excited about it, and I decided to have a nice buzzword to go with it called literate programming, which would then be my way of having revenge on the people who had been talking about structured programming for many years, and thereby making me feel guilty by whenever I wrote an unstructured program. Now I could make them feel even guiltier if they wrote an illiterate program, and so I had this all figured out. And then I decided to launch it in England because there I thought that I was getting people who really could write better. Now, of course, I was joking when I said that, but there is a little grain of truth in this, and namely, as an editor of computer journals, I've found that if I take a random journal article written by someone in Britain that has now been submitted for publication, chances are very good that it's well written. And if I take a random journal article that's submitted for publication from America, chances are very poor that it's well written. And I don't think it's only the genes that control this. There's something else, and it must be something in the educational system or whatever. And that's why I did decide really to talk about literate programming first in the British Computer Journal and then to the British Computer Society. On the other hand, I was glad to see that John Bentley liked it, and he said he would like to popularize the idea and let Americans know about it, and so he wrote this column, which I'm handing out now because I want to talk about literate programming more on Wednesday and Friday. Please read it between now and then. So he first just introduces it, then at the end he has the last piece is the program itself. The last page is the program is a short example of what I hope is a literate program. I wrote it in 2 or 3 hours, but it's still an example that he liked well enough to print. So that's the intro on it. Now, what is the idea? What is the basic idea, though, besides this buzzword of literate programming? And the main idea is that the main idea is to treat a computer program as a piece of literature. To imagine the day when there will be a Pulitzer Prize given for the best computer program of the year. When you write a program, you should think of yourself as an expositor for human readers, not as an instructor of an inanimate computer. This helps greatly, in fact, in making the program better, even for the computer's sake, because you get it right much faster. Every teacher knows that when presenting an algorithm to a class and trying to think of what the steps are as you're at the blackboard or something talking to students, you get much more clarity than if you're sitting there and hacking away and just tossing together some statements, and then you let the computer play around with them for a while. Or if you are doing a one-off program, you usually go through many drafts of it if you do the second way. But but the ones that present to somebody else, when you're actually thinking of explaining it to another human being as you're writing it, you tend to get it right the first time. Now, if you think of I think of myself as a programmer essayist at the same time. I'm trying to explain what it does, and this makes my program better. And I try to explain in this paper some of the ways in which that happens. But then there's a method of actually doing it, and that is to organize a large program as in modules. And everyone knows that the best way to understand complexity is to understand the simple parts of it and to understand the simple ways in which the parts go together. And then you can understand the complex whole. And so you break down a complex program into parts, and then the idea is to explain each part by itself and to explain how the parts relate to each other, and then you've got your program. For this, I remembered the trick about technical writing that I told you about earlier. That is that I try to explain things twice, once formally and once informally. And so that's the style that I decided to freeze into this method of programming, where I would start with an informal description. So every module begins with text and ends with Pascal, ends with formal computer program, but begins with informal text. And these are complementary to each other, just in the way that when you're writing a paper in mathematics that I said earlier, you give a formula and you say the non-increasing vectors, and then you say that these are vectors. Then you give the formal definition of what those vectors are. So I froze that into a style of writing computer programs where a person sits at a terminal and actually you compose this thing. I show you the way it looks on your terminal. It looks like this. And so I have a special control symbol that says I'm beginning a new section. Then I start typing away here, giving the informal comments, and then I get to this special symbol again coming in here, followed by a less than sign, which is going to mean here's going to be the name of that module, and the name of the module is called Program to Print. Okay, take a look at it here now. It's called Program to Print the First 1,000 Prime Numbers 2. This 2 means it's module number 2, and in module number 1. The code was the program to print the first 1,000 prime numbers 2. This number at the end of the module name always tells where to look for the module, like Versal program 4 is module number 4, etc. Other constants of the program 5. So now inside module 2, I have a program here, program to print the first 1,000 prime numbers, and it's given here completely, but this also involves other references to code that goes somewhere else that I haven't written yet, haven't explained yet. This is 543. I'm going to get to them when it's time in the exposition, when a person reading the program would be interested in knowing about the details. But I don't declare everything first the way a compiler needs to know when it reads it. I'm declaring things in the order in which a human being wants to read it. And so this is the idea of the programming system, which is called Web. I guess I told you that we chose Web after a bunch of other names were considered, but based on Roget's thesaurus. Trying to think, and it was one of the few three-letter words that hadn't been used yet for a computer system name that I could find. Web sounds a little spidery and so on at first, but it also has some nice aspects, and we got to like the name Web. In fact, I went to Germany shortly after this trip to England, and I found out that Web was the word for weaving, and the Latin word for weaving is texa. And so everything was coming together. And where am I going? Now at the computer terminal, I sit and type something that looks like this. And and the name of a section tends to be rather long, and so I allow it to abbreviate it in the file. And the computer figures out that this was actually programmed to print the first 1,000 prime numbers, because that longer identifier had already appeared earlier up here. See. So these 3 dots are actually there. I've actually typed those 3 dots. These 3 dots I didn't, though. These 3 dots are an ellipsis that indicate what it would look like. So then I have this computer file written in this style where I alternate between informal and formal, and then so that's called a web file. I have 2 programs that read web files. One of them is called Weave, which converts the web file to a TeX file. Then TeX will print the output, and this actually was printed by TeX. This is the output of Weave. So you take the web file, you weave it, and then you TeX it, and and you get, and this is what you get in output. But there's another branch, and that is you run the Tangle program on the web file, and that produces a Pascal program. The Pascal compiler can compile that and run it. And now that's another important issue, I think, about computer programs. If you're ever going to publish computer programs, that are supposedly running computer programs, the computer has to be in charge of the typesetting. There's just too many things that can go wrong between trying to get everything to be properly transmitted between an actual computer file and somebody going through and typesetting it by hand and typing it what they think is a computer program. Now, see, unfortunately, I didn't save the galleys from this Programming Pearls article, but this was very amply demonstrated on this sample program at the end here. This was typeset. This was typeset by the Waverly Press, and a tremendous number of errors were on the galley proofs, and I caught most of them, and John caught some that I didn't catch, and it was absolutely clear that this method of publishing programs would not work if it required another human being in the pipeline, in the whatever you call it, the loop, between the computer program and the printing press. But it has to be a computer control going from the source to the typesetting in order to get it right. There's just so many chances for errors otherwise, and that's what Weave does. Weave includes the formatting that will insert indentations and boldface and italics and so on according to these conventions of Myrtle-Kellington, and other formatting conventions people like that they can also adopt, and they could build such systems too. This whole idea, it doesn't depend on TeX and Pascal. You could substitute for TeX any typesetting language. You could substitute for Pascal any programming language, and people are developing things like this with Lisp, for example, as a programming language, and there's TROF and C versions that have been developed and so on. The only problem is, I guess somebody has also actually tried to use TeX and TeX to use this system for writing TeX macros, and then we had a little problem as to what to name these files because they both had the same name. Both were named TeX files. But that was the only case. Well, now. So this is an idea that seems to be working reasonably well now. In at least the second last issue of the Communications, this I think it's the September '87 issue now has a new column called Literate Programming or something, which is scheduled to appear 3 times a year, which is based on the reaction to this article that Bentley wrote. He said that there was more mail produced by this article than anything else that they can remember at the Communications, and so it touched a nerve of some sort anyway, that people were looking for better ways to communicate computer programs. Now, what I want to talk about the rest of this week is the experiments that I did earlier this year with 9 undergraduates who were working with me on a research project, and I asked them to write some programs in the web system and see what they went through learning it, because I had only done it myself, using it. My own experience was too personal. I couldn't separate myself from it, and if there was anything about the system I didn't like, I could easily change it. But somebody else gets it, and they might have to fight the system because they don't have the freedom to change it when they want to. And so I want to show you some of the experiments that went on there, the first and second drafts of the programs that the students wrote. That's why. But I'd like you to prepare yourself for that by reading this article. Now, the last few minutes today, I want to say just a couple of things about computer user manuals. Now, we'll say more about it later because everyone knows this is a blight on the industry. I talked to Lyle Nelson of the communications department, and he says, "Oh, he's so glad you have a course on writing in computer science department because the computer manuals I've been reading are so terrible, and in fact it's really scandalous the way manuals come out now. And I was going to try to just bring you a couple of bad examples, but I didn't succeed in finding the worst examples. Now, so maybe if some of you have examples of your favorite terrible errors in user manuals, please bring them to class on Wednesday and Friday, and I'll be able to use them this week or next week. But I want to take up a collection here of really glaring errors in user manuals that you've seen. Now, I have to report that I read the DBase 3 manual that my wife had a year ago, and I thought it was pretty bad, and so I went back to her shelf to get the manual so that I could Xerox some of the pages to show you how bad it was. But they had come up with DBase 3 Plus and the whole brand new manual, and I looked at the new manual, and actually that's probably the first computer manual for a PC that I had ever seen that I thought was actually respectably done, and I couldn't find anything to complain about. In fact, it looked like they had thought about that rather well in this second version. So maybe I should even bring that in as a good example to show. But it was, but somehow bad examples are more fun. So please bring in some bad examples for me to look at. Now, I wanted to make a few general comments here. That most of these manuals are written by somebody who thinks they're trying to write for the absolute novice, and that's reasonably that's a good thing to try, and the only trouble is that it's usually accompanied by a paragraph that says that this is for the absolute novice, followed by another paragraph which makes it absolutely clear that it's not. And here's one that I got in the mail last week. This is a proposed manual for PC Metafont, and it says I like this paragraph very much. It may at times seem in this manual as if we were belaboring a point or repeating ourselves needlessly. If so, please have patience. Keep in mind that you may have a greater knowledge of or ability to learn about computer systems than some other users. However, we're attempting to help everyone discover the rewards and so on. So now, that sounds great. Now the next paragraph, though, says, for text listings, whether they're part of an input file or an output file, the character something shall note the spot where an implied concatenated line exists. The line following that with the concatenated symbol should be considered, it will be indented 2 character widths. Now, I don't understand what the heck the guy's talking about, and I wrote Metafont, and so finally, after seeing a bunch of examples, it was clear that really this is much narrower. They wanted to show lines that are narrower than their page. I mean, wider than their page, and so they wanted to show that something was that's 2 lines in this book is actually 1 line in a file, but that's not what it says here. Now let's see, the time is about up, but I want to show you this anyway. There's a book that came out last week. And it's probably one of the best computer science books of the year. Probably the best. It's by 3 people who 2 of them are excellent writers, it's about the Awk language, which the initials AWK is what of the authors is what led to this. Is what led to this language, and they don't say in their preface, but they tried to write this manual so that it would be for someone who has no experience with other programming languages. And now in the beginning of the preface, so anyway, this was and Al gave a copy of this to my wife so that because it seems like Awk is really the system of choice for her with kind of work that she does on her PC. And so, but when Jill got to the 3rd paragraph, all of a sudden, here it was, or wait, what am I saying here? She knows about regular expressions. She's heard about that term actually before, but here she says, Zach, The action language looks like C, but there are no declarations. Strings and numbers are built-in data types, and all of a sudden, now, of course, the authors, Aho, Kernhan, and Weinberger wouldn't understand that Jill has just one word for declarations and data types, and that is gobbledygook. This sounds like gobbledygook as far as she doesn't know what any of this is. Any computer scientist knows this. Now, and so on the next page it says, why is awk a good language? Because there are no declarations, because storage management is easy. It has the advantages of pseudocode, but they can be run, which is not true of pseudocode. And then there's make programs and all these things. Now, you have to explain this to some class of readers, but there would be, but this completely turned off Jill, and she still is gamely going through the examples in the book. And this book has, by the way, has more than 1,000 examples of awk programs in it, and each one has been tested and run with awk and actually typeset by a computer so that they're correctly transcribed and everything. That's a very fine feature of it. And I think it's a well-written book, even though it suffers from this problem. But this is inherent, no matter what. If you are a person who's been in a field for very long, you won't realize when you're using jargon. But when you're trying to, if you take as a goal to try to write for a novice user, you will at least be writing very clearly to the people who are like you. And this will make your book very much more successful than if you tried to write for a high-level user, and then you would confuse everybody. So I would say even though you might not be able to succeed because you just aren't a novice, it's still worthwhile to try writing for the novice, because then you will very well communicate with the experts, and otherwise you communicate with nobody. So, okay.
Okay, I wanted to start today by giving kind of an overview of where we've been. We've been plowing through some mathematics the last few lectures and see if we can just take an overall picture of where we are. The key theme, of course, is what we've been looking at is the relaxation time approach to the Boltzmann equation. So everything that we've written down the last few times has been based upon that approach. And that approach, as you know, basically says that we can take a time rate of change of the distribution function through the scattering and write it as a difference in f over a relaxation time, which we've then written by definition as a function phi over tau times df naught dE, where we define this function phi times df naught dE as the difference between the distribution function under a driving force and the value at equilibrium. And then the Boltzmann equation was simply this equal to the effects on the distribution of a force as this affects the distribution function as a function of k, and then plus a velocity, and then the effect on the distribution function as a function of space. And our job then was to see what the implication was for this expression, what our solutions might be ultimately for phi, and hence what our solutions would be for the change in the distribution as a function of what kind of a perturbation or a driving force we applied. So we worked this through, we saw how to express these and so on, and we came up with a master equation which we wrote down as this. It involves the term P, which was just a shorthand for a combination of terms, an electric field term, and then a term involving a temperature gradient, we could write as gradient log T, and then for completeness, the gradient of E minus EF itself. That term was dependent upon electric field through this term and a temperature gradient through this term. And this term, as we saw, would be 0 for either an electric field only or a temperature gradient only, but might well appear if we had other kinds of spatial gradients. That this P dot V was then just given by, we added to that then, we added another term, QH squared, bringing now the magnetic field in general. We had the gradient of E with respect to K cross the gradient of phi with respect to K. And this then was equal to phi over tau. So this general equation is reduced down, and what we were doing then was trying to see what the solutions were to this equation as we looked at what kind of variables we put into it. Now, we did three main variables, of course. One of these was the electric field only, and we did a little bit more with that than with the others. So the results summarizing for the electric field would be that we saw that if we had an electric field only, that then this phi function was given by minus tau q E dot V. Looking at this in a little bit more detail, a little bit earlier on, we had seen that we could write down the distribution function f in terms of this kind of formulation as the equilibrium function now plus tau q ex vx df naught dE. And that the current density in this picture was given by a term involving the electric field, the free carrier density, the effective mass, and kT, and an average of the relaxation time times e to the 3/2 times f naught times 1 minus f naught dE, the equilibrium distribution function, 1 minus the distribution function, over the integral of e to the 1/2 F naught dE. In other words, looking at electric field only, with this being the general solution of the equation we just talked about, this would be the distribution function. We put that in, we calculate the current using this distribution function. We got this result, and that led us then to the conclusion that for a semiconductor, for example, if we use spherical equal energy surfaces to enable us to write it in this form, that then the current density would just be given by Q squared EX n over m star times an average value of the relaxation time, and that this average value of the relaxation time was essentially given by integral like this, which was, we could rewrite, so it looked like a normal average as being tau e to the 3/2 F naught dE over the integral from 0 to the maximum energy. These integrals, of course, were over partially occupied bands, 3/2 F naught dE. So this was the expression for the semiconductor, and it told us that we now knew how to calculate the average value of tau of E, and that would bring in temperature dependencies and so on, which would be important for our discussion of things like mobility. In the metal case, we saw that there could be a first-order solution, which is very simple, namely that the average value of tau was just equal to tau at the Fermi energy, because that's where the scattering action was taking place. There was also a second-order solution, which we derived, and which I won't bother to write down again now, which takes into account the exact way in which the conductivity varies at the Fermi energy. So that was our main result for the electric field only. This result for the distribution function. Now, this result for the phi function, and hence distribution function, gave rise then to this expression for Jx, which we also, you remember, wrote in terms of a transport integral, K1, for completeness. That this transport integral, this K1, expressed this kind of integral we're talking about here in a general way. And if we just write down what its general value was again, remember, transport integral Kn was defined as minus star. We have the integral of tau of E, n of E, e to the nth, dF naught dE dE, as we wrote it down for spherical equal energy surfaces. That this was a general useful average because of the way that these various integrals were formed, and that we could, using this notation, therefore simply describe the current density, which we see written in a simple form this way, also in terms of this integral, if we simply express that symbolically in terms of this transport integral. So that was one kind of result. Now, the other result that we saw from the E only, the interpretation of this was that the effect on the distribution function could be described by behavior that looked like this. If we look at the distribution function as a function of K, that the effect of applying electric field only was to shift the distribution function in one direction in K space, all points shifting in the same direction, and by an average amount that was given by, or by an amount that was given by Q Ex tau over H bar. That this was the change in distribution function, and similarly we could look at the equal energy surfaces and see that this corresponds then to them, if we had spherical equal energy surfaces, for instance, them shifting by this same amount in K space, in Kx, Ky space. So that was the picture of